Okay, let's talk about complexes. Okay, so continuing our conversation with the transition metals and some of the compounds that these transition metals will form. Okay, we're going to take a look at complexes. For the complex, we have a central metal atom, and it's bonded to a group of molecules or ions. In this case, we see the ammonia, and then we also see the chloride ion. And these are bonded to that central transition metal. If the complex that is formed by this transition metal and the ions and molecules attached, if it has a charge, we're going to call that a complex ion. So, complex ion is kind of a subset of a metal complex. If this ion forms a compound, say by bonding ionically with a ion, then you create a compound that is called a coordination compound. So really these complex ions kind of act the same as your polyatomic ions. In that they will bond with other ions. So in the complexes, the ions or molecules that bond with that central transition metal are usually anions or polar molecules. What you're looking for this ligand is really an unshared pair of electrons. And these unshared pairs, it's thought that they take advantage or they fill in the empty d orbitals that are available around those transition metals. Okay, so, and remember, with these coordination with the coordination compounds made up of complex ions and other ions, you're going to get a wide variety of different ions and complexes, even from the same metal. You may be saying to yourself, what did that sentence mean? All right, so if you take, for example, we look at this formula. The components that are inside the brackets make up the complex ion. If this is soluble in water, if I put it in water, I'm going to get my complex ion, okay, and that would have a +3 charge, okay, and then I will also get 3 chloride ions for the one that is circled. Okay, so anything inside those brackets, that is the complex ion, okay, and if it is soluble in water, that will stay as the complex ion, and it'll break apart just like a polyatomic, just like an ionic compound that contains a polyatomic will break into the polyatomic ion, and then whatever ions are bonded to it. Okay. As we learned previously, many of these are brightly colored. It is the polar and ionic. It's the polar molecules and the ions that are part of the complex ion that form that electric field that then splits that d sublevel into a lower energy orbitals and higher energy orbitals. And remember, an electron will move from a lower to a higher, absorbing a certain wavelength. Whatever wavelengths pass through, the complementary color is what we see or what our eyes perceive. Werner's theory, this is not all that important to know. The concepts behind it are important, right? You will be asked to identify the oxidation number for the metal. Okay? So if we look at this molecule, I should say if we look at this complex ion, we see that we have cobalt. We have 1, 2, 3, 4 ammonia molecules, and we have 2 chloride ions. Well, these ammonia molecules are neutral. Okay, all right. These 2 chlorides, though, I have 2 negative charges. My overall charge on my complex ion is a +1. Hopefully you can figure out what the cobalt charge needs to be, so that when I add it to the -2, I'm going to end up with this overall +1. So the idea is, what does the charge on the cobalt have to be? Okay, so that when I add those 2 negatives, I'm going to get the overall charge of +1. Hopefully you can see that that needs to be a +3. Okay. So that is what Werner called the primary valence, and it is looking at the oxidation number for the metal. Basically, you look at the metal, you look at what is attached to it as ligands. Some of those ligands may have charges. You compare those charges and the overall charge on the complex ion, and then you should be able to figure out what the charge is on the transition metal. Okay. Secondarily, you are going to be asked to identify what the coordination number is. This is actually fairly straightforward. The coordination number is the number of atoms directly bonded to the metal. So you identify your metal. I have 1, 2, 3, 4, 5, 6 ligands. The coordination number then is 6. That's really all there is to it. So you do not need to know that Werner called them primary and secondary valences, but you do need to be able to calculate the oxidation number for the metal, and you do need to calculate the coordination number for the complex. So the central metal and the ligands directly bonded to it make up what's called the coordination sphere. In this compound, COCl3 with 6 ammonias, all 6 of the ligands are the NH3, and the 3 chloride ions are outside the coordination sphere. Right? Now, when you look, what he's talking about is really this first one. Okay, so again, I view it as anything within these square brackets is your complex ion. Okay. The 3 chlorides are what make up the coordination for the complex compound. I so said that wrong. It's a coordination compound. Oh. If we look at their next example, that would be this one. In the brackets, or in the coordination sphere, I have 5 ammonia groups and 1 chlorine. Those other 2 chlorines or chloride ions are outside of the sphere. Okay, and again, what you'll see is whatever's inside the sphere, that making up the complex ion, will be inside the brackets. That will stay together if I put it in water, and the other ions would break up, again, similar to what a polyatomic compound would do, right? Or what an ionic compound with a polyatomic attached to it would do. Okay. Looking a little closer at the actual structure, and again, this is going to be like looking at the shapes. If we look at a coordination compound, I'm sorry, this would be a complex ion with 3 chlorines, and it actually means 2 chlorines, and 4 ammonias. You can see one structure would look like this, and one structure would look like this. They are different because look at the orientation of the 2 chloride or chlorines, chloride ions to each other. We haven't covered acids and bases yet, okay, but what we're looking at, there is a definition of a Lewis acid and a Lewis base. Lewis bases have non-bonding electrons. A Lewis acid has empty orbitals. So a Lewis acid is also known as an electron pair acceptor, and a Lewis base is known as an electron pair donor. And hopefully you can see here, if I have silver, and it is going to make a complex ion with 2 ammonias, you can see the 2 ammonias each have this lone pair that then fills in an empty orbital of silver, making that complex ion. That metal-ligand bond, hopefully it makes sense that it's going to affect its physical properties, color, chemical properties, and ease of oxidation. Let's get into some of how do you calculate what the oxidation number is. Again, you're going to probably be looking for what the oxidation number is on the transition metal. You're going to look at the ligands. Ammonia you should know is neutral, so even if I have 4 of them, it's 4 times 0, that is 0. You look at the overall charge of the complex ion, which is +2, and you kind of back calculate what does the copper have to be so that when added to 0, I get +2. And you can figure out the copper has to be +2. Looking at another example, okay, we're given this if you know that copper is a +3, it has 4 ligands of water, but each of those is 0. It has 2 chloride ions. That would be +3 +0. 2 chloride ions minus 2, you have a complex ion charge of +1. Just a definition. It's called a donor. The atom of the ligand that supplies the non-bonding electrons is known as the donor atom. Hopefully that would be pretty apparent. And then the number of those atoms is the coordination number. So really the number of things bonded to the transition metal is equal to the coordination number. Some metals typically always have the same coordination number. All right, cobalt and platinum are 2 of them. I guess chromium 3 is also, cobalt 3 is that as well. At this level, it's sometimes, we don't know enough to be able to predict how these metals are going to form these complex ions. So just keep in mind that the most commonly encountered are 4 ligands and 6 ligands, or a coordination number of 4 and a coordination number of 6. Those are the most common. So if there's no other information available, assume that it's either a 4 or a 6, and then proceed with the problem that way. Since we just got done talking about VSEPR, we're going to spend a little bit of time talking about the geometries. There are 2 if I have a coordination number of 4. That would be a tetrahedral and a square planar. You should be familiar with these shapes. The most common is 6 ligands, and that shape is octahedral, and hopefully that shape looks familiar to you from the extended octet conversation. I'm going to quickly go through some things that you're not necessarily responsible for, but it's kind of cool. Okay. Some ligands actually have 2 donor atoms. Okay, those are called polydentate ligands or chelating agents. And one of those is ethylene diamine. Okay, and you can see both, oh, I need a pen. Both of these nitrogens have a unshared or an unbonded pair. Okay, and this is showing this entire ethylene diamine molecule. And you can see one end of the molecule is one ligand, and then the other is the other ligand. Okay, so it makes this big complex thing. Okay. And there's even one that has 6. I'm not even going to try to say that, and mercifully it is abbreviated EDTA. That has 6 donor atoms. So you can see that this graph, it like wraps all the way around that transition metal. I just thought that was kind of cool, so I wanted to share it. Okay. And there's a bunch of polydentate ligands. Okay. Chelating agents, they really render metal ions inactive and to keep them in the solution, but they just kind of tie them up so they can't do anything. Phosphates are typically used to tie up calcium and magnesium ions to prevent them from interfering with detergents. Okay. We're going to talk just briefly about isomers. Isomers are compounds that have the same molecular formula, but their atoms are arranged in a different order or in a different arrangement where it can't they're locked in that different orientation. Okay. So briefly, structural isomers are isomers that differ in what ligands are bonded to the metal and what is outside the coordination sphere. Those are called coordination sphere isomers. Not really all that important, and hopefully just looking at these structures you can see that they're all the same things involved, but they're in a different arrangement, and that changes some of the properties, most notably the color. It also does change some of the chemistry, some of the chemical properties of them. One thing that is somewhat important to note is that we have things called stereoisomers, and these are geometric isomers, and they differ in where the different ligands are located. Cis isomers, this would be an example of a cis isomer here, where the 2 things that are similar are on the same side. Cis, I kind of, in my head it means same to me. Okay, trans is where they are on opposite sides. Okay, so a trans isomer is on opposite sides, and again this will affect the chemical properties and physical properties of the compounds. Okay. All right, and again just going back into the color and why that happens. And that should be the end of my screen cap.